turns out to be really convenient in many applications to find a formula for the sum of a geometric sequence. The sum of the terms of a geometric sequence would be called a what? It would be called a series. We use S subscript n to represent the sum of the first n terms. So symbolically, Sn would be given by A1, the first term, plus the second term, plus the third term. So A1 plus A2 plus A3 plus dot, 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 all the way until you get to the nth term, A sub n. And in summation notation, you could say that's equal to k equals 1 to n of, so the sum from k equals 1 to n of A sub k. So, and this symbolism works for any series. It's generic. It doesn't have to be geometric or arithmetic to use this symbolism. Now, we're going to assume that this kth term formula, whatever it is gives geometric terms or generates a geometric sequence. That's the assumption. So if you write out Sn then, if you write out Sn using the nth term formula that we just developed, you get A1. So I'm going to write out this longhand version, but put in what those terms should be in terms of the nth term formula. A1 plus, really you can think recursively here, it's A1, the second term is A1 times R. The third term is A1 times R squared. Fourth term is A1 times R cubed plus dot, dot, dot. The nth term is A1 times R to the n minus 1. That's the formula we just developed for the nth term, right? Does that seem reasonable? Now I want to show you a good trick then for getting a nice compact plug and chug formula for Sn. It's pretty tricky. Remember when I showed you how Gauss probably added the first 100 counting numbers together? It's kind of a trick like that, a little bit like that. So what we're going to do is we're going to take this sum, which we're calling Sn here, and we're going to multiply by R. So on the left side, I'll multiply by R. On the right side, I'll multiply by R. But if I multiply a finite sum by R, what can I do with that R? So I'm not going to show the work here other than to show you this real quick. So I'm going to multiply both sides by R. What do I have to do with this R? Distribute, right? So keep going. Okay. So I don't actually want to write that right there. I want to write it below. So it becomes, okay, A1, if I multiply this entire right side by R, I get A1R. Now I'm going to slide that over and line it up with its like term. And then I multiply A1 times R times another R, I get A1R squared. And then I multiply A1R squared by R, I get A1R cubed. And I'm just lining up like terms. I keep doing that. Okay, well, little timeout here. I want to multiply A1 times R to the n minus 1 by R as well. So what do I get? What do the laws of exponents tell me that I get when I multiply by R? It's really R to the 1, right? So what's the rule for multiplying like bases, base R's? You keep the base, and what do you do with the exponents? You add, remember that? So like x squared times x cubed is x to the 5th. So we're doing the same thing here. R to the n minus 1 times R to the 1 is R to the n minus 1 plus 1. So what's going to happen to the minus 1 here and the plus 1 here? They're going to cancel out, and you'll have A1 just R to the n, right? Does everybody buy that? Okay, so that's what I get when I multiply this guy by R. So the guy I multiply before this, however, the guy that comes before this term in the sum, that's the one that slides over to match up with this guy. And then when I multiply the last guy by R, I don't have anything to line it up with. So I just have plus a1 times r to the n on the end. There's nothing to match it up with. It's an extra one that I get when I multiply the last term in Sn by r. Okay. Dwell on that for a second. Meditate on that. Does that make sense? Okay, so remember what I'm doing. I'm trying to get a sum here, a sum formula here, where there's no dot, 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 plus dot, dot, dot involved. So is there anything I can do with those quantities to get a bunch of cancellation, to get the dot, dot, dots to go away? Can you think of, so think of these as two equations, Sn and r times Sn. What could I do with the bottom equation to the top equation? I could subtract, couldn't I? Isn't that a neat trick? So think of subtracting. It's like when you solve systems of equations, the elimination method. Think of subtracting the bottom equation from the top equation. Now, do you see what happens when I do that? I distribute this negative so that each one of these terms becomes negative. So you could either subtract or add the opposite. That's the same thing. Now you can see then when I add, I end up canceling every single term in between the a1 and the minus a1 times r to the n. Everybody see that? Okay, so on the left side, I'm left with Sn minus r times Sn. On the right side, I'm left with a1 minus a1 times r to the n. So now I just need to solve for Sn. So on the left side, how do I get a single Sn? What can I do? I can't add because of the r here, but I can factor out the Sn, can't I? What would be left if I factor out the Sn? It would be 1 minus, remember there's a factor of 1 in everything. So if I factor out this Sn, there's a 1 left here. If I factor out this Sn, there's a minus r left here. So 1 minus r left inside. Whoops. The right side doesn't change. Oh, except I think I might as well go ahead and factor out the a1. It'll maybe look a little nicer. If I factor out the a1, what's left on the right side? 1 minus r to the n. So now I want to solve for Sn. These guys are connected by multiplication. What do? Divide by 1 minus r. Both sides. Cancel, and I'm left with just Sn. So let's write it down. Sn then is equal to a1 times 1 minus r to the n over 1 minus r. This would be the sum of the first n terms of a geometric series. So it's the finite sum formula for a geometric series. Now there is going to be an infinite sum formula, so that's why I wrote down finite right there.